Mastering algorithm development, a strategic approach to building efficient solutions in today's data-driven world. Efficient algorithms are the backbone of modern software systems. From optimizing search queries to enabling real-time analytics, the ability to develop robust algorithms is critical in solving complex computational problems. The journey from conceptualization to implementation requires meticulous attention to both theoretical foundations and practical applications. This guide explores advanced strategies that will help developers create high-performance algorithms tailored to specific needs. Fundamental principles of algorithm design. At its core, algorithm design involves transforming abstract problem statements into executable code through well-defined steps. Understanding key principles such as time complexity analysis, space efficiency considerations, and correctness verification forms the foundation of successful algorithmic solutions. A solid grasp of these fundamentals enables programmers to make informed decisions during the development process. For instance, choosing between O, n, and O, log n, time complexities can significantly impact system performance when dealing with large datasets. Time complexity assessment helps predict how an algorithm's execution time grows relative to input size. By analyzing big O notation, developers gain insight into potential bottlenecks before writing any actual code. Evaluating space requirements ensures optimal memory usage while maintaining acceptable runtime characteristics. Balancing these trade-offs often determines whether an algorithm achieves its intended purpose effectively. Divide and conquer, breaking down problems into smaller subproblems that can be solved independently, then combining their results for final solution. Greedy approach, making locally optimal choices at each stage with hope they lead to globally optimal outcome. Dynamic programming, storing intermediate results to avoid redundant computations across overlapping subproblems. Backtracking, exploring possible solutions incrementally while abandoning paths that fail constraints early. These paradigms provide structured approaches to tackling different types of problems efficiently. Selecting appropriate techniques based on problem structure leads to better performing implementations. For example, dynamic programming excels in scenarios with overlapping subproblems where previously computed states can be reused rather than recalculated repeatedly. Iterative refinement process in algorithm development. Creating effective algorithms rarely happens in single iteration. Instead, it involves continuous refinement through testing, profiling, and optimization phases. This iterative process allows developers to identify weaknesses and enhance overall performance systematically. Initial prototypes typically focus on functionality over efficiency. Once basic behavior is validated, subsequent iterations prioritize improving speed, reducing resource consumption, and ensuring reliability under various conditions. Profiling tools play a crucial role here by highlighting hotspots, areas consuming disproportionate amounts of processing power. Identifying these enables targeted optimizations without rewriting entire codebases unnecessarily. Optimization efforts must balance between making meaningful improvements versus getting bogged down in premature micro-optimizations that offer negligible benefits. Empirical evaluation techniques. Benchmarking serves as essential method for comparing algorithm effectiveness against alternatives. Carefully designed experiments allow objective comparison of different approaches using standardized metrics. To ensure reliable evaluations, tests should be run multiple times under controlled conditions. Randomized inputs help prevent bias towards particular cases that might not reflect typical usage patterns. Measuring wall clock time provides intuitive understanding of performance differences but may vary based on hardware specifics. Using CPU cycle counts offers more consistent measurement across different platforms. Memory profiling complements timing measurements by revealing how much working set size changes with varying input sizes. This information helps assess scalability characteristics accurately. Analyzing time complexity through practical examples. Consider sorting algorithms as case study. Bubble sort has O, n superscript 2, worst case scenario, whereas merge sort maintains O, n log n, regardless of input order. Actual benchmarking confirms these theoretical predictions while also showing constant factors affecting real-world performance. While asymptotic analysis gives general idea about growth rates, empirical testing reveals constants hidden within big O notation. These constants become significant when implementing algorithms at scale. For instance, Quicksort's average case performance matches MergeSort's theoretically superior worst-case performance despite having same asymptotic bounds. Real-world benchmarks demonstrate that sometimes theoretically worse algorithms perform better due to lower overheads. This highlights importance of combining theoretical analysis with experimental validation when evaluating algorithm suitability for particular applications. Design patterns for scalable algorithms. Developers face increasing demand for scalable solutions capable of handling growing workloads. Recognizing common architectural patterns helps build adaptable algorithms that maintain efficiency even as data volumes increase exponentially. Distributed computing models enable parallel processing by dividing tasks among multiple nodes connected via network infrastructure. MapReduce paradigm exemplifies this approach by separating computation into mapping phase followed by reduction step. Stream processing frameworks handle continuous flows of incoming data instead of batch-oriented processing. Apache Kafka and Apache Flink represent popular technologies facilitating low-latency stream processing capabilities. Caching mechanisms reduce redundancy by storing frequently accessed results temporarily. Effective cache eviction policies ensure limited storage capacity doesn't become bottleneck itself. Pipelining improves throughput by allowing next operation to start before previous completes entirely. This technique finds application in database query optimizers and graphics rendering pipelines alike. Error handling and robustness considerations. Building resilient algorithms requires anticipating edge cases and designing defensive mechanisms to handle unexpected situations gracefully. Proper error detection and recovery strategies minimize risks associated with faulty input or environmental disruptions. Input validation routines verify format and range constraints before proceeding with core computations. Sanitizing user-provided values prevents injection attacks and other security vulnerabilities. Exception handling structures define clear pathways for managing failures without compromising program stability. Structured exception propagation allows higher-level components to respond appropriately to errors originating from lower layers. Graceful degradation features ensure continued partial functionality even when ideal conditions aren't met. Degraded mode operations maintain usability while alerting users about limitations caused by current circumstances. Code quality assurance practices. Maintaining clean, readable codebase enhances long-term maintainability and facilitates collaboration among teams. Following established coding standards promotes consistency across projects developed by different contributors. Version control systems track changes made over time, enabling rollback to previous versions when necessary. Branching strategies manage concurrent developments without disrupting stable release lines. Automated test suites validate correct functioning after every change. Unit tests verify individual functions while integration tests confirm compatibility between different modules. Code reviews serve dual purpose of quality assurance and knowledge transfer between team members. Here feedback helps catch issues that automated checks might miss. Performance optimization strategies. Identifying bottlenecks through profiling guides optimization efforts toward most impactful areas first. Prioritizing changes that yield highest return on investment avoids wasting resources on minor gains. Data structure selection dramatically influences performance characteristics. Choosing right representation for given use case reduces unnecessary conversions and accelerates access patterns. Memory management practices affect both speed and stability. Reducing allocation/deallocation frequency minimizes garbage collection pauses which can disrupt real-time operations. Leveraging hardware-specific optimizations can extract additional performance from available resources. Vector instructions and SIMD extensions accelerate certain mathematical operations significantly. Documentation and knowledge sharing. Comprehensive documentation becomes critical asset for future maintenance and extension of algorithmic solutions. Well-written comments explain rationale behind non-obvious implementation choices. API references document function signatures, parameters, and expected behaviors precisely. Version history tracks modifications along with reasons motivating those changes. Visual aids such as flowcharts and diagrams clarify complex logic flows that might otherwise be difficult to follow solely through textual descriptions. Knowledge-sharing sessions foster collaborative environment where best practices get disseminated organically among team members working on similar challenges. Conclusion: algorithm development is multifaceted discipline requiring careful consideration of numerous interrelated aspects. Successful implementations emerge from thoughtful combination of sound theoretical foundations with practical engineering skills. By adopting systematic approach encompassing rigorous testing, thorough evaluation, and continuous improvement cycles, developers can consistently produce high-quality algorithmic solutions meeting demanding performance requirements.